All right, we're doing 1 through 11 for the first part of homework today. Oops. We're going to start. Sorry, I got to get this ready. We're going to start with our cofunction identities. So we just filled these in on our notes today. Anytime you see a weird angle, that should be the first thing you replace in any of these problems. So right here, cotangent of pi over 2 minus x. What is that equal to? So its cofunction is tangent x times cosecant x. When we have a mix of trig functions, we switch to sine and cosine. So tangent is sine x over cosine x. That's the quotient identity. Cosecant is 1 over sine x. That's the reciprocal identity. The sine x's can cancel. 1 over cosine x is secant x, which is what we were trying to prove. Same idea on this side. So what is the secant of pi over 2 minus x? That's the cosecant of x. Divided by what's the tangent of pi over 2 minus x? That's the cotangent of x. And this is also supposed to come out as secant. So let's see. So 1 over sine x. And we're dividing by cotangent. So that means we're dividing by cosine x over sine x. So you can flip this around. 1 over sine x can get multiplied by sine x over cosine x. So the signs cancel. And again, 1 over cosine x is secant x. All right, this next one has a bunch of large exponents, so we should think about factoring this. All right, so looking at the left side, it's much more complicated than the right. You have two terms right here. 1, 2. So the question is, what is the GCF? Now, I guess you could multiply this together. This could be secant to the 7th. Maybe we'll do that. This could be secant to the 7th, x, tangent x, minus secant to the 5th. Maybe this is easier to see. X times tangent x. So all I did was like multiply this together. You're not distributing, by the way, because there's no addition. It's just multiply these three things. So I multiplied the two like bases together. Okay, and then this might be a little more clear. What is the GCF? So both of these have a secant to the 5th x at least and a tangent x. And so if you divide each term by secant to the 5th tangent, you get secant squared x from the first term minus 1 from the second term. This is a rearranged Pythagorean identity. Secant squared minus 1 is equal to tangent. Tangent squared, excuse me. And take a look at what we're trying to get here. We're trying to get secant to the 5th x, and this does multiply to tangent to the 3rd power x, which finishes our proof. Now, number 4 is the same idea. You still have a GCF on this side. And I just want to remind myself, like, where does the square root come from? Remember, that's the same thing as the sine to the 1/2 of x. So we're looking to get cosine cubed sine to the 1/2. So what's the GCF here? They both have sine to the 1/2, at least. Remember, with GCFs, you take out the smaller of the two exponents. So they both have sine to the 1/2. They both have a cosine x. Okay, so if we take that out of the first term, we get 1 minus 5/2 minus 1/2 is sine to the 4/2, which is sine squared x. And 1 minus sine squared is cosine squared. So we have sine 1/2 x, sine to the 1/2 x times cosine x times cosine squared x. And just to copy this side, so that is cosine to the 3rd power x if I multiply those together. And the sine to the 1/2 can be rewritten as square root of sine x. All right, Negative angles. So again, if you see negative angles, you should start on that side and take care of those negative angles first. So look at your even and odd identities. Cosecant of negative theta is equal to negative cosecant of x, and secant of negative x is equal to secant of x. Its cosine and secant are the only ones, because they're even functions, they're the only ones that the negative goes away. And then let's change to sines and cosines. So negative 1 over sine x over 1 over cosine x. Flip that around, negative 1 over sine x times cosine x over 1. Negative cosine x over sine x is negative cotangent x. All right, on number 6, take care of this negative angle first. So I'm not going to do anything besides rewriting that. Sine of negative x, this will become 1 minus sine x. We're trying to get cosine squared. You should have it pretty well in your head by now that cosine squared is 1 minus sine squared. If I'm sort of seeing this, we've used that rearranged Pythagorean identity a lot now. If not, keep rewriting your proofs. The best thing you can do is keep rewriting your identities, so that you really have those down and memorized, and it makes this a lot easier. I'm going to FOIL these together. So when I FOIL these conjugates together, I get 1 minus sine squared x, and that equals cosine squared x. On to number 7. Let's get rid of these negative angles over here. So this becomes cosine x over 1 minus sine x. We've had this problem a few times now. This particular one might even be without the negative angles. It might be in our notes packet. But what we do when we get a fraction that's already in terms of sine and cosine and it's not a complex fraction, we multiply by the conjugate. Multiply by 1 plus sine x, top and bottom. You don't actually multiply the non-conjugates together, just to save yourself time. So you're going to have to go back and factor the cosine out if you distribute it through. You do multiply the conjugates together. 1 minus sine times 1 plus sine is 1 minus sine squared x. We just saw that in the last problem. 1 minus sine squared x is cosine x. Is cosine squared x. I'm sorry, I don't know why I keep dropping that. 1 minus sine squared x is cosine squared x. This cosine can cancel with one of the cosines down here. 1 plus sine x over cosine x. Now, what am I supposed to be getting? I'm supposed to be getting secant x, which remember is 1 over cosine x. Tangent x is sine x over cosine x. So you have that. You just have to show, oh yeah, this can be separated out with the Hart method, which is really just saying if you're dividing a bunch of terms on top by one single term, then you're allowed to divide them separately. You're like undoing a common denominator, basically. And that is secant x plus tangent x. All right. Let's start the same way by getting rid of our negative angles. So this is going to be 1 minus cosecant x. Cosine of negative x is just cosine x. Cotangent of negative x is minus cotangent x. Because I have a mixture of different trig types, I'm going to change them all to sines and cosines. So 1 minus 1 over sine x. Cosine x just has to stay. Cotangent is minus cosine x over sine x. This is a complex fraction. Remember, you can save a lot of time by using this shortcut on complex fractions. Instead of doing the math up here, doing the math down here, flipping the bottom fraction and seeing what cancels, you can just say the denominators are sine, so I'm going to multiply by sine over sine. And that's equal to 1 times sine x is sine x. 1 times 1 over sine is minus 1. Cosine times sine is cosine times sine. And cosine over sine times sine is going to be minus cosine. We're trying to just get secant x, which is just 1 over cosine x. So let's look at this. What else can we do here? In the denominator, you can factor out a cosine x. So sine x minus 1 on the top, factor out a cosine x, which leaves you a sine x minus 1 on the bottom. So those cancel. 1 over cosine x is secant x. Make sure that you're writing your angles as you're doing your work. Okay, this one looks kind of crazy with its x's and y's. That's not a typo there. Everything's sine and cosine, but these are not common denominators yet. So the first thing to do is set up the common denominators. So the common denominator is sine x plus sine y times cosine x plus cosine y. Now, I'm not going to spend any time foiling that together because 2 reasons. It's going to be ugly. Nothing's going to cancel. Also, I'm just trying to get 0. So in a fraction, to show that a fraction is 0, you're just trying to show that the top is 0 and the bottom can be whatever. So don't bother foiling that out. You are going to need to multiply and actually foil on the top. But we're multiplying conjugates the way this is set up. Cosine x plus cosine y times cosine x minus cosine y is cosine squared x minus cosine squared y. So that's that first part. There's a plus in the middle. The second fraction will get multiplied by sine x plus sine y, top and bottom. So again, conjugates. Sine x times sine x is sine squared x minus sine squared y. We're supposed to show that this is 0. So how do we do that? First of all, cosine squared x and cosine squared y do not cancel each other out. They're different angles, but cosine squared x plus sine squared x is 1, and minus cosine squared y minus sine squared y is minus 1 over the denominators. And 1 minus 1 is 0. So I didn't bother foiling in the denominator because you can see I didn't need that for anything. Okay, next one. Let's start on the left side here. Now, this problem can be really long or really, really short. So I like to use the heart method whenever I can before going straight to sines and cosines. So there is one term, even though there's 2 parts to it. This is one chunk here. There's no addition or subtraction. So I am allowed to divide each part in the top by tangent cotangent. That means that I'm allowed to make this tangent x over tangent x cotangent y plus cotangent y over tangent x cotangent y. That's really convenient because it cancels out a pair of tangent x's and a pair of cotangent y's. So you're left with 1 over cotangent y plus 1 over tangent x. Always do little quick checks on what the right side's supposed to be. I still don't want to switch to sine and cosines. I want to use reciprocal identities, which I rarely use with tangent and cotangent, but in this case it makes sense because 1 over cotangent y is tangent y, and 1 over tangent x is cotangent x. So that finishes that proof. This takes a lot longer if you change everything to sine x, cosine y, vice versa. There's a lot of stuff to get everything to cancel and clear out that complex fraction. So I do not advise going that way. Okay, last one that we're doing today, and we're back to a co-function identity. So remember, having a sine squared right here is the same as having the squared out here. So you can say the sine of pi over 2 minus x is cosine, and then we're squaring that. So you're allowed to make this, you're allowed to make this cosine squared plus sine squared, and that's equal to 1. Gosh, that was a super short proof. All right. The second half of this worksheet we are saving for tomorrow. If you want to get a head start on it, feel free.